Okay, hi everybody. Let's do today's lecture about relativity. So first we'll do the special theory of relativity, and then we'll do the general theory of relativity after that. Okay, so first thing, all motion is relative. The place from which motion is observed and measured is a frame of reference. That's important. An object may have different velocities relative to different frames of reference. To measure the speed of an object, we first choose a frame of reference and then pretend we are in that frame of reference standing still. Then we measure the speed with which the object moves relative to us, that is, relative to the frame of reference. Isn't there some reference frame that is still? This is a common question. And the answer is no, we can never find a frame of reference that's still. They're all just relative. Okay, so here's some postulates of the special theory of relativity. All laws of nature are the same in all uniformly moving frames of reference. The speed of light in free space has the same measured value for all observers regardless of the motion of the source or the motion of the observer, that is, the speed of light is a constant. So this says all laws of nature are the same in every reference frame. And then this one says the speed of light is the same everywhere. Okay, so let's get the idea of space-time. And then you guys can read this. The important thing is this ratio down here. The speed of light is the same in every reference frame. And so space and time are related. They shrink and expand depending on the situation so that c is constant. C is the speed of light. So we think of space and time as interrelated, and they shrink and warp and expand and contract to make c the same everywhere. Okay. Also, there's the idea of simultaneity. Let's just read this here. Two events that are simultaneous in one frame of reference need not be simultaneous in a frame moving relative to the first one. So that means if we have a simultaneous event in one frame, it's not necessarily simultaneous in another. So a good example of this is we have a guy in a rocket ship, and he sees light coming from a light bulb, and the light from the light bulb hits the back wall and the front wall simultaneously. But if the rocket is moving and a person on Earth is looking at the rocket, then the light will hit the back wall first before it hits the front wall in their frame of reference. So something simultaneous here is not simultaneous here. And this isn't just a quirk of light. This is actually, things are actually not simultaneous here, and they are here. So it's really weird. Okay, is the non-simultaneity of hearing thunder after seeing lightning similar to relativistic non-simultaneity? So yes, it's not exactly the same. No, it is a completely different phenomenon. That sounds good. It depends on the thunder. No, so it's B. So it's completely different. Okay, suppose that the observer standing on a planet sees a pair of lightning bolts simultaneously strike the front and rear ends of the compartment in a high-speed rocket ship. Will the lightning strikes be simultaneous to an observer in the middle of the compartment in the rocket ship? So this is the situation. The observer on Earth sees two lightning strikes simultaneous. So if we go up here, this observer sees lightning strikes simultaneous. Two lightning strikes happen simultaneously here. So if we look from the rocket ship's perspective, they might not be simultaneous. In fact, they won't be. So yes, they will be simultaneous. No, they will be non-simultaneous. It does depend on how not simultaneous, depends on how fast the ship is moving. If the ship speed is 0, they will be simultaneous relative to the Earth. It depends upon how long the ship is. That's not important. So it's B. Okay. Time dilation is the speeding up and slowing down of time so that speed of light stays the same in every reference frame. So if you're in a ship, let's look at this picture here. If we have a light bouncing up and down in the ship on two mirrors, then the light travels this distance here. But for an observer on Earth, the light has to travel up and down, but it's also moving laterally. So this path right here and this path right here this one is longer. So because this one is longer and the speed of light is the same, then from this person's perspective, time is going more slowly in here. Whereas for this person, time is going normal, and this person looks like they're going slowly. Okay, and this is all because the speed of light has to stay the same, yet the distances the light travels are different. Okay, So more about time dilation, that we can calculate and measure time dilation. For calculations, we use the Lorentz factor. So this Lorentz factor is pretty complicated here. It's gamma equals 1 over square root 1 minus the speed of the object squared over the speed of light squared. This is always it's always greater than 1. And t naught here, that's the proper time. That's the time this guy experiences. And t here is the time that the observer on Earth sees the rocket ship's time go. Okay, so and we can summarize this in this formula: that t observed equals gamma times proper time. So the person on Earth observes slower time on the rocket ship, and the person in the rocket ship experiences proper time, normal time. So the observed from Earth equals gamma times the proper time. And this is a graph of gamma. So important right here is bold. Clocks will tick slower and slower as the spaceship approaches the speed of light. So the gamma blows up here, and the clocks on the ship, according to the person on Earth, get slower and slower and slower as the rocket ship goes up in speed. Okay, if you were moving in a spaceship at high speed relative to Earth, would you notice a difference in your pulse rate or the pulse rate of people on Earth? Let's read that again. If you're moving in a spaceship at high speed relative to Earth, so you're in the spaceship moving high speed, would you notice a difference in your pulse rate or the pulse rate of people on Earth? So your pulse rate would feel normal to you, but the pulse rate of people on Earth would look really slow. So you would notice a difference in both pulse rates. I think you'd notice a difference in the Earth's people. You would notice a difference in your pulse rate. That's not true. It would feel normal. You would notice a difference in the pulse rate of people on Earth, but not your own pulse rate. That sounds good. You would not notice a difference in either pulse rate. So I think C is the best answer. Okay. Will observers A and B disagree on measurements of time if A moves at half the speed of light relative to B? So yeah, so they have to disagree. They're moving at different speeds. Their measurements of time are going to disagree. So let's see. Yes, they would agree completely. That's false. No, they would disagree completely. That's probably true. They would agree half the time and disagree half the time. I don't think that's right. D, none of the above, so it's got to be B. They would disagree completely. Their understanding of time's movement would be different because of their different speeds. Will observers A and B agree on measurements of time if both A and B move together at half the speed of light relative to Earth? So they're moving A and B. They're both moving together at half the speed of light relative to Earth. So they're moving at the same speed, hopefully the same direction. Okay, if that's true, then they would agree completely on the speed of light. So that's A. Okay, contrast to this, they're moving at different speed, they disagree on time, same speed, they agree on time. Does time dilation mean that time really passes more slowly in moving systems, or only that it seems to pass more slowly? So it's actually moving more slowly. Time really passes more slowly in moving systems. That's right. Time only seems to pass. No, that's not right. Depends upon how fast the system is moving. Yeah. How slow time is does depend on how fast it's moving. But the idea that it's real or not is irrelevant. This is irrelevant to that idea. It depends on the direction in which the system is moving, not for time. The direction is not important. So time really does pass more slowly in moving systems. Okay, there's the twin paradox. And the twin paradox is you have two twins. You send one off in a rocket ship. So according to the person on Earth, their time is moving slowly. They turn around, and the person on Earth ages. When they come back, the person in the rocket is younger compared to the twin who stayed on Earth. This is a paradox because shouldn't they both age at the same time? And the answer is no. And the reason is when the rocket leaves, this is the better picture right here. So the rocket leaves Earth. Let's see here. So this is Earth. What do I got here? I got this thing. Okay, this is Earth. This is the rocket over here. Okay, when the rocket leaves, okay, they're moving relative to one another. And this turns around. That's important. And then it comes back. And when they reconnect, the two twins are different ages. The one that was on the rocket is younger than the one on Earth. The important thing is that at the turnaround point, things change. okay? Because the turnaround point, when this rocket turns around, it's moving through many different reference frames. And so that causes the difference. Okay, so there's time dilation the whole way there. Then there's funkiness because of the turnaround, because it's moving through reference frames. Then there's time dilation all the way there, all the way back. And that means that the person in the rocket ship will be younger than the person on Earth. Okay. All right, so let's get some questions about this. The ship sends equally spaced flashes every 6 minutes while approaching the receiver at constant speed. How will these flashes be spaced when they encounter the receiver? Okay, so let's go through this picture here. So this is the rocket ship heading away from Earth. And this is the one twin brother, this is the other twin brother. If it sends out light, if the rocket ship sends out light pulses, they become spaced out and compressed on the other side. And then after it turns around, the light pulses become compressed. Let's look at this picture here, and spaced out here. So when the rocket ship is heading towards Earth, the light pulses Earth sees are compressed. And when the rocket ship is heading away from Earth, then the light pulses Earth sees are extended. Okay, so the ship sends equally spaced flashes every 6 minutes while approaching the receiver at a constant speed. So it's approaching is important. So the rocket ship approaching Earth is going to see compressed light pulses. How will these flashes be spaced when they encounter the receiver? So if they're compressed, it's going to be less than 6 minutes. So not equally spaced. They'll be not equally spaced 6 minutes apart. They're going to be equally spaced less than 6 minutes apart because they're compressed. So B. Okay. Since motion is relative, can't we say as well that the spaceship is at rest and the Earth moves? In which case the twin on the spaceship ages more. And the answer is no. And that's because of that turnaround. So we have the Earth twin and we have the rocket ship. Rocket ship comes up. It's not symmetric because of the turnaround, and the rocket ship comes back to Earth. So we can't say that the twin on the spaceship ages more because of the turnaround. So no. And I say the situation is not symmetrical. Okay, time dilation. More about this. This time dilation, I think this is supposed to be length contraction. We just talked about time dilation. Now we need to talk about length contraction. So length contraction takes place only in the direction of travel. If an object is traveling horizontally, no contraction takes place vertically. So this is baseball. If it's moving horizontally here to the right, then as it approaches the speed of light, it gets thinner and thinner and thinner in the direction of travel. Okay. Then there's relativistic momentum. So we've got this gamma factor, which is way back up here. Anytime we see this gamma factor, we're talking about this Lorentz factor. So before momentum was equal to mv, now it's equal to gamma mv. That means that as we get closer to the speed of light, momentum gets much, much higher than we would have predicted with Newtonian mechanics. Okay, and we can call this like a stiffness of the trajectory. If the momentum of the electrons were okay, so let's go through this experiment here. So if we accelerate an electron beam and we want to deflect it with a magnetic field, if we only predict with this formula, then the momentum will be greater, and the electron beam will be deflected less than we would have predicted with Newtonian mechanics, which is this dashed line. So if we read this, if the momentum of the electrons were equal to the Newtonian value, gamma mv, the beam would follow the dashed line. So that's what they're talking about here. I think this is supposed to be mv here. So that's supposed to be mv. So if the momentum were equal to the Newtonian value, the momentum would be less than we thought, and it would be the dashed line. If we use gamma mv, it would be the solid line, which actually happens. Okay. There's also mass energy and equals mc squared. So mass and energy are equivalent. So we can calculate the energy in a particular mass by multiplying by c squared. But we can also find the equivalent mass that something is of the same of energy. So light, for example, is affected by gravity because energy and mass are equivalent. We'll get to that later. Okay, this is also responsible for when we convert mass to energy in a nuclear reaction. we get lots of energy out because we convert a little bit of mass multiply this huge number, c squared. Okay, so let's talk about general theory of relativity. It was postulated, Einstein postulated in 1905 that no observation made inside a closed chamber could determine whether the chamber were at rest or moving with constant velocity. Okay, so here we're leading into that acceleration and gravitational fields are the same. Einstein thought that the laws of nature should be expressed in the same form in every frame of reference, accelerated as well as non-accelerated. So special relativity is constant velocity frames of reference. Here it's accelerated frames of reference. Okay, and this leads to the principle of equivalence, that accelerations are equivalent to being in a gravitational field. Okay, so I think the important thing is, let's look at this picture. So we've got two pictures. We've got Einstein in each one. If the rocket isn't firing its engines, he's free floating in space, and everything inside the chamber is floating. If the rocket fires its engines, he's now accelerating. The whole thing is accelerating up in this picture. And he feels everything is stuck to the ground because of the acceleration of the rocket, which is exactly equivalent to what we feel in a gravitational field. So acceleration and gravitational fields are the same. Well, they're equivalent. Okay, so here's another picture. Let's look at this picture here. So this person in this rocket ship is accelerating upward. So when she drops the balls, they fall relative to the rocket, which looks like gravity. She drops the balls. They actually stay in place whilst the rocket ship accelerates up towards the balls. But from her perspective, it looks like the balls fell to the ground like normal gravity. So this is another example of acceleration and gravitational fields being equivalent. So let's look at this. The principle of equivalence states that the observations made in an accelerated frame of reference are indistinguishable from observations made in a Newtonian gravitational field. Okay, if you drop a ball inside a spaceship at rest on a launching pad, you'll see it accelerate to the floor. That's at rest on a launch pad, so you're on Earth. Far away from Earth, how else could you see the ball? How else could you see the ball do the same? Well, since gravitational fields and accelerations are equivalent, the spaceship should be accelerating at g to get the same effect. Okay, we can also apply this to light. So just like with the balls, with the rocket coming up to meet, in this case, light, the rocket, if light goes into a rocket, say it comes into this gap here, comes into the gap, as the rocket accelerates upward, the light falls not on the opposite side of the opening, but down here. So if we're in the rocket's perspective, the light came in here and bent down here. So that means that if accelerations and gravity are the same or equivalent, then light is bent by accelerations. That means it's also bent by gravity, which is what we see. Okay, so let's look at these pictures. Just keep looking at the pictures. Okay, so light comes in here. It hits a glass sheet in the middle. Well, it's gonna, if the opening is exactly in the middle of the glass sheet, then after the light hits the glass, it'll be slightly lower than the midpoint, and then it'll hit the end point here. Okay, and then this is where the trajectory is this dashed line, whereas the top dashed line is the horizontal. Okay, so I think this is the exact same thing as this. So light is bent by gravity. And we see this is a picture of a warped picture of a galaxy by this dot here, because light is bent by gravity. Okay, and let's look at this. According to the principle of equivalence, if light is so deflected by acceleration, it must be deflected by gravity. How so? Einstein's answer: light is massless, but it's not energyless, so equals mc squared. Gravity pulls on the energy of the light because energy is equivalent to mass. Okay, we learned previously that the pull of gravity is an interaction between masses, and we learned that light has no mass. Now we can say that light can be bent by gravity. Isn't this a contradiction? And we said, no, it's not a contradiction, because of E equals mc squared and mass energy equivalence. Okay, why do we not notice the bending of light in our everyday environment? Bending of light never occurs anywhere. That's not true. It's always occurring. Bending of light does not occur in our everyday environment. It only occurs in outer space. That's not true. It's occurring all around us. There is bending, but it's very minute and not perceptible to us. That's the best answer, C. Okay, gravity, space, and new geometry. Okay, so what this is telling us is for our everyday understanding of geometry, we live in a Euclidean world where everything makes sense. So right angles, squares have right angles, triangles, angles add up to 180, and everything is flat. However, we don't live in that world. We live in a world where the space-time we live in is actually not flat and warped. So if this is flat space-time here, this triangle, these triangles' angles add up to 180. But in this warped space-time here, these triangles add up to more than 180, those angles. And in this space-time, the triangles' warp angles add up to less than 180. So we live, almost all of our lives are lived in very approximately flat space-time. All the geometry is normal, Euclidean geometry. But with gravity, it's not quite that. And these warpings do occur. Okay. So general relativity calls for new geometry. It's non-Euclidean geometry, warped geometry. Space is a flexible medium that can bend and twist. Okay. The presence of mass produces the curvature or warping of space-time. So mass, okay, say we have a planet or the sun, it warps the space around it, and that is gravity. Okay, and that means we're not in this flat space-time anymore. We're in one of these warped situations. So masses respond in their motion to the warping of the space they inhabit. Space-time near a star is curved in a way similar to the surface of a waterbed when a heavy ball rests on it. Okay, so this is the cartoon picture here. We have a heavy ball resting on a waterbed that then bends the waterbed down, and then objects respond to that as if it was gravity. Okay, so let's do some questions. What Einstein discovered about space and time is that they are separate entities. No, are linked. That's important right there. This doesn't make any sense. This is Newton's gravitational law. Are special to today's space travelers. Well, that's not even a thing. So linked. Einstein stated that the laws of physics are, well, we know he wants them to be the same in every frame of reference. So we're looking at that. Different in different situations. We don't want that. Common sense applied to microscopic and macroscopic things. Well, that's sort of true, but often it can be wrong. The same in all frames of reference. That sounds good. The same in all uniformly moving frames of reference. So he wants in special relativity, it would be uniformly moving frames of reference. In all frames of reference, uniform or accelerating is this one. So I think this is the best answer. Oh, so this is, if we're talking about special relativity, this is the answer. Okay, so they must be talking about the laws of physics and special relativity. Einstein's second postulate tells us that the speed of light, well, we know it's constant everywhere. Depends on one's frame of reference. No. Is constant in all frames of reference. Provides accurate clocks. Yeah, that's actually true. Slows in transparent medium. That's also true. But the second postulate is about the constancy of the speed of light. So the second one. Compared with events that occur simultaneously in a particular reference frame, events occurring in another reference frame will be seen as simultaneous also. Maybe, maybe not. May or may not be seen as simultaneous also. That's true. Because if they're moving at the same rate, they'll see things as simultaneous. If they're moving at different rates, they may not be simultaneous. Will not be seen as simultaneous, that's not necessarily true. So it's got to be this one. Okay. When we speak of time dilation, we mean that time compresses with speed, stretches with speed, is constant in all speeds. Well, that's not true. Is related to space. It is related to space, but we're talking about time dilation. That's how speed changes time. We know when something moves faster, the time clock ticks more slowly. Time moves more slowly on moving objects. So I think the best description there is stretches with speed. Okay. Inside a rocket ship traveling at enormously high speeds, you would notice your companions in the ship. Well, if you're all in the ship, you don't really notice anything different than normal life. So you don't age differently because you're all in the rocket ship. You wouldn't even notice, there's no noticeable compression in the rocket ship. You're all in the rocket ship. Slightly more massive? No, we're all in the rocket ship moving together. So it's got to be none of these. Okay. You are looking into the past when you look at distant stars, distant planets, your image in a mirror. So all of them. So even though the image in the mirror is almost now, light does take some time to travel from the mirror, from your eyes to the mirror and back. So technically you're seeing the images in the past. So it's all of these. As a blinking light source recedes from you at high speed, you see the frequency of flashes. So as something moves away, then the frequency of the flashes decreases. And this is called redshift. So it's decreased. And the picture is the picture of the spaceship moving away from Earth. From the Earth's perspective, if they're giving off flashes of light, then those flashes of light hit the Earth at a decreased rate. When you return from high-speed space travel, you find your stay-at-home friends, well, they're going to be older. Okay, that's the twin paradox. Pretend that a starship is somehow traveling at c relative to Earth, and it fires a drone forward at speed c relative to itself. The speed of the drone relative to Earth is, well, the speed of light can never be exceeded, and it's the same everywhere, so it's got to be c. Okay. When we speak of length contraction, we mean that the length of things, well, as things get faster, things compress. So compress with speed. When an observer at rest watches a high-speed spaceship, objects on the ship appear shorter in the direction of travel, that sounds good, shrunken uniformly, that's no good, shorter in the direction perpendicular travel, that's not right, longer in all directions, so it's going to be shorter in the direction of travel. Compared with the Newtonian momentum, P equals mv, the momentum of an object traveling at great speed is greater by a factor of gamma. Gamma is always greater than 1, so it's not less, it's not no different, so it's got to be the first one. A beam of electrons hits a screen after being bent by a magnet. Due to relativistic effects in the magnetic field, the beam bends. Okay, this is kind of a weird question. So it's going to bend less because it has more mass, but it only has more mass compared to our Newtonian idea of physics. So if we make a prediction with Newtonian physics and we make a prediction with relativity, our Newtonian physics will be wrong. And Newtonian physics will have a beam bent more than relativity. So our relativistic particle will bend less than Newtonian mechanics. But there's two predictions. The universe does what it does, so it's going to be less. According to special relativity, you on Earth watching a high-speed spaceship would notice. Okay, so we're on Earth and we're watching a high-speed spaceship. So on the spaceship, clocks on the ship are running slow. That sounds good. We know for fast-moving things, clocks run slowly. People on the ship aging more quickly. That's false. Because if clocks running slow, they would be aging more slowly. Masses of things on the ship decreasing. Well, that's not true. The masses are going to be going up because of the gamma factor. So it's going to be clocks on the ships running slow. And all of these definitely not true. To say that E equals mc squared is to say that energy increases as speed of light squared. Well, no, because speed of light is constant. Is twice as much as the speed of light. Well, that's not true, because that would be 2mc. This is mc squared. Energy and mass are equivalent. That sounds good. Equals mass traveling at the speed of light squared. Mass can't travel at the speed of light, so it's got to be energy and mass are equivalent. When everyday low speeds are inserted into the relativity equations for time, length, and momentum, the equations correspond to Newtonian physics. That is good. That's true. Don't work. That's not true. Work only by inserting a gamma factor of gamma. That's not true. None of the above. It's got to be Newtonian physics. So Einstein's theories of special and general relativity, they predict beyond Newtonian physics, which means they must make the predictions of Newtonian physics and high-speed physics near the speed of light. So when everyday speeds are used with Einstein's ideas, it corresponds to Newtonian physics. According to the correspondence principle, so this is the correspondence between Einstein's theory and Newton's theory. New theory must agree with old theory where they overlap. That sounds good. Newton's mechanics is as valid as Einstein's mechanics. That's not true. Newton's is for low speed, Einstein's is for all speeds. Relativity equations apply to high speeds, while Newton's equations apply to low speeds. That's not true. Relativity equations apply to all speeds, Newton's equations apply to low speeds. Special relativity and general relativity are two sides of the same coin. That's not true. Special relativity is constant velocity frames of reference. General relativity is with acceleration and gravity. So this is the best answer. Okay. The correspondence principle tells us that, okay, it's kind of the same question. Newton's and Einstein's physics are one and the same. That's not true. Mass and energy are one and the same. Well, that's true. That's true. There's an equivalence, but that's not what this is. Special relativity and general relativity both say the same thing. That's not true. New theory must agree with old theory where they overlap. That sounds good. Okay. So that would be Einstein's new theory must agree with Newton's old theory where they overlap at low speeds. Einstein's theory of general relativity came 10 years after he published special theory. That's true. It's part of his special theory. No. So general relativity is more general than special relativity. Nicely fits inside the special relativity now. So it's special relativity fits inside general relativity. So it's going to be the top one. Okay. Which of these would comprise an accelerated frame of reference? A child riding a merry-go-round, so that's circular motion. That's accelerated. A train rounding a curve at constant speed. So rounding a curve means velocity is changing. That's acceleration. Oh, both of these. That looks good. What exactly is equivalent in Einstein's principle of equivalence? It's got to be space and time are not equivalent, but they're related. Gravity and that's the one. Gravity and acceleration are equivalent. Gravity and energy, no. Mass and energy, there's an equivalence there, but specifically Einstein's principle of equivalence is gravity and acceleration. Drop a ball while accelerating upward in a moving elevator, and the floor comes up to meet the ball. Oh, I forgot my equivalence principle. I should have read the answers. So ball meets the floor. That's true. Floor comes up to meet the ball. So it's sort of an acceleration, or a gravity picture, or an acceleration picture. Either of them are good. Forgot my equivalence principle. Shine a horizontal beam of light in an upward accelerating elevator, and the beam misses the point it would hit if the elevator were at rest because the beam curves due to gravity. That sounds good. Elevator moves up while the beam moves horizontally. That sounds good. Either of these. So I got to remember correspondence principle. So either. General relativity is the most concerned with gravity. Okay. General relativity predicts that light slows down due to gravity. Okay, sounds good. Light bends in gravitational fields. That sounds good. Clocks slow in gravitational fields. That sounds good. So all of these. Okay. Measurements of time involve relative motion, gravity, both of them. So gravity tells us, general relativity tells us how gravity affects time. Special relativity tells us how relative motion affects time. Sunlight can be bent as it grazes the sun due to atmospheric refraction in the sun's atmosphere. That's not related to today's topic, but that sounds true. The sun's gravitational field, that's general relativity, says that's true. So both of them. Okay. According to four-dimensional geometry, the angles of a triangle can add to, so if it's four-dimensional flat, then the triangle angles will be 180. If it's four-dimensional geometry that's warped, it could be more or less than 180. So it could be all of these. It's one of them, but we don't have any constraints on it. It's going to be all of these. Space-time is curved by not enormous forces, quantum fluctuations. Mass is the big one. Vacuum, I don't know what these other things are. So mass. General relativity predicts that light leaving the sun is speeded up by gravity. Not sure about that. I don't think that sounds right. If the light is leaving the sun, then the light will travel at c. It's not sped up or slowed down by gravity. Light passing the sun is deflected. That sounds good. A clock on the sun's surface runs slower than on Earth. I'm not sure if that's true or not. It sounds true. Because if you're closer to a stronger gravity, your clocks run more slowly. Objects shrink in in their direction of motion. Well, that's special relativity. I don't think light is sped up or slowed down by gravity. Light passing the sun is deflected. That sounds like a good one. Not sure about this one. Let's find out. Yeah, so light passing the sun is deflected. If a star that is 100 light years from Earth explodes, gravitational waves from the explosion would reach Earth in 100 years. Okay. Because gravitational waves travel at the speed of light. Since light has no mass, how can gravity deflect it? Well, we know that there's the energy mass equivalence. So photons don't have tiny mass. Light takes on mass when it interacts with matter. That's not true. Gravity doesn't and has no effect on light. That's not true. The space through which light travels is curved. There we go. That's the right answer. Newtonian and Einsteinian gravity are one and the same. That's not true. Compatible with each other in weak fields. That's true. At odds with each other. That's not true. They're compatible in weak fields. So it's this one. Okay, and that's it. And that is the last lecture for the semester. So the midterm is, not the midterm, the final will be 1 week after the quiz for this is be the Wednesday next week. Let me get the date on that. It'll be on 5/5. Sorry, that's today. It'll be on 5/15. So I'll see you guys then. Okay.